In this lesson, we're looking at finding optimum volume and surface area, so maximizing volume, minimizing surface area, things like that. But first, we're going to do a quick recap of the main concepts from the investigations in your last lesson. So firstly, you should have noted that for a fixed perimeter, the rectangle with the largest area has equal dimensions. So in other words, it is a square. So for example, if we had 20 meters of fencing and we were going to arrange that fencing into some sort of rectangular fashion, there's lots of different ways we could do that. But if we wanted the largest area, we would need to construct that fencing into a square. So we would take the 20 meters of fencing and divide it by 4, which tells us that along each side we would have 5 meters of fencing. And then the area of that enclosure would be 5 times 5. So the largest area we could enclose would be 25 square meters. Then in a later part of that investigation, you were looking at what would happen if one side of the enclosure was bounded, so say along the side of a building, and then we want to enclose this area here. So when you only require fencing along 3 sides, what we do is we take half of the fencing and put it along the length. So if we had 20 meters altogether, we would put 10 meters here. So let's just make a note. In this case, half of the fencing goes along the length. And then the remaining fencing would be split along the 2 widths. So in this case, the largest area we could enclose would be 10 times 5, or 50 square meters. Now these concepts can be extended to maximizing volume and minimizing surface area, so that's what we're going to look at now. So for example, a company might be interested in these concepts if, say, they're trying to design a package and they want to hold a certain amount of product, but they want to save money, and of course less packaging means cost savings. So that gives you one idea of where these concepts would apply. There's of course lots of others. So it says here, for a square-based prism with fixed volume, the prism with the smallest surface area has equal dimensions, so much like with the square, except in 3 dimensions we would call that a cube. So for example, a box in the shape of a square-based prism is to have a volume of 64,000 centimeters cubed and a minimum surface area. So the box needs to hold 64,000 cubic centimeters, but the surface area needs to be a minimum. If we wanted to design such a box, we would want the shape of the box to be a cube. Okay, so if we draw a cube, what we know is that for a cube, the length and width and height are all equal. So let's say x represents those dimensions. They're all the same, so we'll label them all with an x. And we know that the volume of a cube is length times width times height. So that tells us that x times x times x has to equal 64,000. X times x times x is x cubed. So in order to solve for x, we need to take the cube root of 64,000. Whoops, sorry, extra 0 there. Cube root of 64,000, so x is 40. So therefore, the box is 40 centimeters by 40 centimeters by 40 centimeters. Now similarly, for a cylinder with fixed volume, the cylinder with the smallest surface area has a diameter equal to its height. So in other words, diameter equals height. We can also say then, since diameter is the same as 2 times the radius, we can also say 2 times the radius has to be the same as the height, depending. So for example, it says find the volume of a cylinder with a radius 2 meters and height 16 meters, first of all. So let's recall the volume of a cylinder is pi r squared h. So if we put in those values, pi times 2 squared times 16 is about 201 meters cubed. Now in part B of this question, we're asked to find the height and radius of a cylinder that has that same volume, but which has the minimum surface area. So remember we said if we were trying to minimize surface area, then we need to make sure the height is twice as long as the radius, or the same as the diameter, in other words. So in our formula for volume, we're going to replace the volume on the left side with 201 meters cubed, but we're trying to change the radius and height so that we have a minimum surface area. So on the right-hand side, we've got pi r squared. Now, instead of writing h, I'm going to replace that with 2r. Because now I have an equation with one variable, and I can solve that now. When I had 2 variables in the equation, there's lots of different combinations of numbers that would give me a volume of 201 meters cubed, but I'm looking for the dimensions that will give me a minimum surface area. So now that I have an equation only dealing with one variable, we can simplify this on the right-hand side to 2 pi r cubed, which is approximately 6.28 r cubed. Now in order to get r by itself, let's divide by 6.28 on both sides. So r cubed is approximately 32. And now to get r by itself, we're going to need to take the cube root of 32. Your calculator has a button for doing that. If you're not sure where it is, just let me know and I'll help you find it. So the radius we need is approximately 3.17 meters. That means the height will be double that. So the height needs to be, let me try that again. The height needs to be 6.34 meters. So therefore, the radius is 3.17 meters, and the height is 6.34 meters. Now, if you're working with a fixed surface area, so say we had a fixed amount of packaging or a certain amount of cardboard, for example, and we were trying to design a container that would maximize the volume. That's a similar but different type of question. So the next property is for a square-based prism with a fixed surface area, the prism with the greatest volume has equal dimensions. So in other words, it is a cube. Okay, so once again, now it says, suppose you have 1,000 centimeters squared of cardboard, and we're going to use that to make a container to hold popcorn. Find the dimensions of the container, which has to be in the shape of a square-based prism, okay, that will hold the most popcorn. So we have a fixed amount of cardboard. We're trying to maximize the volume. So once again, then, our shape needs to be a cube. So whether we're trying to maximize volume or minimize surface area in 3 dimensions, we want our prism to be in the shape of a cube. And if it's a cylinder, we want our height and diameter to be as close to each other as possible, if not exactly equal. Okay, so for our cube, I've labeled the length, width, and height with x's again because we know they would all be the same because it's a cube. Now, this one's just a little bit different because we're given the surface area. The surface area is 1,000 square centimeters. So that means that each face of the cube has an area of 1,000 divided by 6 square centimeters. There are 6 faces on a cube, so if the total surface area is 1,000, then each face, like each face of the cube, here's one of them, would have 1/6 of that area, if that makes sense. So that would be 166.7 square centimeters. That will help us find x, because remember the dimensions of this square are x times x. So now I know that x squared, the area of that face, is 166.7 centimeters squared, so x has to be the square root of 166.7, which is approximately 12.9. So therefore, the container should be a cube. Whoops. Cube with side length 12.9 centimeters. Now to end the lesson, we have a summary of what you should remember from the lesson. So the minimum surface area for a given volume of a rectangular prism occurs when the height is equal to the side length of the base, so a cube. Also, the maximum volume of a rectangular prism for a given surface area occurs when the height is equal to the side length, once again, a cube. And for cylinders, the minimum surface area for a given volume of a cylinder occurs when the height is equal to the diameter, or again, the height is twice the radius. And that concludes this lesson.